Alright, so we had just finished covering some calorimetry last time, and I would like to go ahead and look at Hess's Law. Now, Hess's Law basically states that the sum of a series of processes, or if there are a number of processes that can be added together, Hess's Law essentially states that the overall enthalpy change for a process is equal to the sum of the enthalpy changes can't spell today. Enthalpy changes of each step in the process. Okay. So the overall enthalpy change for a process is equal to the sum of the enthalpy changes of each step in the process. So, it's number 6 says, consider the following hypothetical reactions. A goes to form B. And the enthalpy change for that process is a positive 30 kilojoules. Furthermore, it then says B goes to form C. And the enthalpy change for that process is equal to 60, positive 60 kilojoules. This uses Hess's law to calculate the standard enthalpy change for A to C. Now, basically, how could you get these equations to add up to A goes to form C? It's actually really easy in this case because you can add them up directly. I know I need A in the product, I know I need A in the reactant side, and I know I need C in the product side. There's precisely one A on the reactant side, so I need one A on the reactant side here. So I leave this equation just as it is. I need exactly one C on the product side, so I leave this equation exactly the way it is, and I add them up. When I add them up, I get A plus B goes to form B plus C. Of course, if anything is present on both sides of the reaction, you can cancel it out. So the B cancels out. So it effectively turns into A goes to form C. So, because the overall enthalpy change for a process is equal to the sum of the steps of the process, since adding these two equations gives me this, that means adding the enthalpy gives me the enthalpy for the overall process. In this case, it's 90 kilojoules. Now it says construct an enthalpy diagram for the substances A, B, and C and show how Hess's law applies. This is a little bit more tricky to visualize, but essentially what it comes down to is this. So here's your enthalpy, and here is your I guess you'd say time. The reaction coordinate, or the time of the reaction. So when the reaction starts out, let's say you're starting with A, right? Usually there's some sort of activation energy, some minimum amount of energy that you have to get before it'll transition from reactant to product. Now the product of the first step is B. So you'll get some sort of activation energy, and then you get this substance B. This is the transition state at which point the reactant is turning into the product. Okay? And then from B, it's 60 kilojoules per mole. So first of all, I want to label the difference in kilojoules per mole between A and B. This enthalpy change is positive 30 kilojoules per mole. And it's actually one direction, it goes up, so that's why it's positive 30. It's an increase from A to B. Okay? Next, B is going to also undergo a change. Of course, B, the change is going to be a little bit more extreme because it's going to be a 60 kilojoule change. At this point, you have the final product, C. And from B to C, there's a positive 60 kilojoule per mole change. So from A to B, it's 30 kilojoules per mole. From B to C, it's 60 kilojoules per mole. So the overall enthalpy change for the reaction ends up being 90 kilojoules per mole. Does that make sense? And next semester in Gen Chem 2, you'll talk a little bit more about this activation energy and how it affects rate of reaction and reaction kinetics. But for now, in thermochemistry, we're satisfied just talking about the changes in energy. All right, cool. So let's do a slightly harder problem, perhaps not just slightly. Number 7. Next. It gives us 3 reactions. It says, given the following data, that N2 plus O2 goes to form NO2. Rather, NO, my bad, 2NO. And it says the delta H for that process is equal to positive 180.7 kilojoules. And then it says a second reaction, so I'm going to call this reaction 1 and reaction 2. For the second reaction, 2NO reacts with O2 to form 2NO2. This gives you a delta H of negative 113.1 kilojoules. Number 3, we have 2N2O goes to form 2N2 and 1O2. And the delta H for that is negative 163.2 kilojoules. Now it's asking me, what is the enthalpy for the overall, for the following reaction? And it says, use Hess's law to calculate the delta H for this reaction. So the reaction that we're looking for, the reaction of interest that we're looking for is N2O plus NO2 goes to form 3NO. And we want to find the delta H of that. So the question is basically asking us to rearrange these three equations up here to figure out what you have to do with these to get them to add up to this. The easiest way to approach this is to look at the reaction of interest, the one you're trying to find the delta H for, and to approach it substance by substance. So what I mean by that is, the first substance in the reaction of interest is N2O. Which of these equations has N2O? The third one. Is that the only one that has it, or is it present in others as well? Okay, that's the only one. Okay. So I know that all of the N2O in the overall reaction must come from this third equation. How many N2Os are in this reaction?
2.
Well, in this reaction?
Oh, that one? 1.
1. But here there's 2, right? So what do I have to do to this equation to make it match this?
Times 1/2.
Times by 1/2. So, reaction number 3, I'm going to modify by multiplying it by 1/2. So that's going to turn this into N2O goes to form N2 plus 1/2 O2. Now, if I multiply the equation by 1/2, as I did here, what does that do to the delta H?
This will be times 1/2 too.
Yeah, it'll be times 1/2 as well. So 163.2 divided by 2 is going to give us negative 81.6. Okay? Now, next I'm going to look at the second substance in the overall reaction that I'm trying to find. NO2. Now, which of these equations has NO2 in it? Just the second one, right? And is it that's the only one that has it, right? Now in the equation number 2, NO2 is what? It's a product. But in the overall reaction, it's a
Reaction.
So what do I have to do with this?
Flip it.
Flip it. Also, how many NO2s are in this reaction?
2.
And how many in the overall?
1.
So what else do I have to do?
Multiplied by 1/2.
Exactly. So for this equation, number 2, because I need only 1 and it has 2, and because it's on the wrong side, I have to both flip the equation and multiply it by 1/2. When I flip the equation, it's going to be NO2 on this side, but it's going to be half as much because I'm multiplying by 1/2. So NO2, and then I need half as much of this, but on the product side, so half of 2NO is just going to be NO, and half of O2 is going to be 1/2 O2. That means equation number 2 is taken care of. Now I have to look at the final substance that I need, and that is the NO. Now there's a couple of different ways to solve this one at this point. Since I know I need NO, the easiest way is probably to figure out how many NOs I need. Because I can't change these anymore, right? Because these are giving me things that I know that I already need. I can't modify these at all. But if I added these up, how many nitrogen monoxides, how many NOs do I have on the product side so far?
1.
1, just this one, right? So I need how many more?
2.
2. Now, the equation that has NO in it that has not been tampered with, because remember, we've already messed with 2, so we're not going to use this one. The equation that has NO in it that hasn't been tampered with is equation 1. What would I have to do to this equation to get 2 more NOs on the product side? Nothing. Just leave it exactly the way it is, right? So I'm going to go ahead and take my equation 1, and I'm going to write it precisely the way it already occurs. N2 plus O2 goes to form 2NO. Now the delta H for that is not going to change. It's still going to be positive 180.7 kilojoules. And the delta H for this one, because I flipped it, what does that do to the sign here?
Flips it.
Turns it positive. And I also multiplied it by 1/2, so I'm also going to have to
Half.
divide by 2, yep. So the delta H for equation 2 becomes positive 113.1 divided by 2, which, when you calculate that in your calculator, that should give you
56.6.
Yeah, 56.55 or 56.6. Right. Positive. So, at this point, I can add up all of my equations to see if they do indeed add up to this overall equation. Does it indeed add up to the overall equation? Let's find out. So I have N2O plus NO2 plus N2 plus O2 goes to form N2 plus half O2 and half O2 gives me a whole O2 plus 1 plus 2 is 3 NOs. Now what cancels?
N2s.
N2
O2.
and O2. So what's left, does that give me the overall reaction? Yeah, it does.
Okay.
That N2O and NO2 goes to form 3NO.
Yeah.
These are in fact indeed what I'm left with. So that does match the overall equation. And because it does match the overall equation, that means I can add up these as well. So I'll add up my delta H's. I add up negative 81.6 plus 56.6 plus 180.7. And what does that give me?
55.7 kilojoules.
You mean 155.7?
Yeah, 55.7.
Oh, okay. I thought you said 55.7. I was going to say, you might be a little bit off if it was just 55.7. And no, that's good. That's good. I think you. Does that make sense? These Hess's Law problems tend to be very difficult for students. I'm not sure if it's just because of the way that they're explained or what, but if you take the reaction that you're looking for, the overall reaction, if you're taking this and you're matching only one substance at a time to an equation, then you're usually okay. As a general rule, if a substance appears in more than one equation, skip it. Don't do anything with it and go to the next substance. If you have to deal with it later, then you can deal with it later. Okay. So let's do a little bit of calculation with another manifestation of Hess's Law that requires you to use standard data. Number 8 says, calculate the value of delta H for each of the following reactions. Okay, I'll go ahead and put reaction A up on the board. N2O4, gas, plus 4H2 gas, goes to form N2 gas, plus 4H2O gas. Now you might be wondering offhand if it's really necessary to include the phases, and I'm here to tell you that yes it is, because if this is H2O liquid versus H2O gas, the delta H changes significantly. Okay, so in this case, we're still using Hess's law, but instead of having equations, we end up using standard enthalpies of formation. So, what is an enthalpy of formation? What is a delta H of formation? So, a enthalpy of formation it's important to know the definition. Because you ought to know what you're using. An enthalpy of formation is the enthalpy change accompanying the formation of precisely one mole of a substance from elements in their standard elemental state. Okay, so the enthalpy change accompanying the formation of precisely one mole of a substance from elements in their standard state. So what is standard state? Do you know?
The state that is most common in nature.
And while that's true, standard state has a couple of very important principles. Standard state has a pressure of 1 atm, and a standard state temperature, so this is the pressure at standard state, and a temperature of 25 degrees Celsius. So standard state means that you have a temperature of 25 degrees Celsius and a pressure of 1 atm. Okay? So the enthalpy of formation is the enthalpy change accompanying the formation of precisely one mole of a substance from elements in their standard elemental state. Their elemental state at 1 atm and 25 degrees Celsius.
So it's kind of different from SDP.
It's different from SDP. SDP is 0 degrees Celsius and 1 atm. The pressure is the same, but the temperature is different. Yeah?
Would this also be like the 760 mmHg kind of thing?
Yeah, 760 milliliters of mercury is the same thing as 1 atm. Alright, so in this case, the enthalpy of formation of any element in its standard state is, of course, 0. Because how much energy does it take to get from an element in its standard state to an element in its standard state?
0.
Nothing, yeah, it doesn't cost anything. So, are any of these elements in their standard state?
N2.
H2. Hydrogen in its standard state is a gas. So this has an enthalpy of formation of 0 kilojoules per mole. And what? Anything else?
N2.
N2. And the delta H of formation of nitrogen is 0 kilojoules per mole. Alright. Now, in the chart, the table below, it says the delta H of formation of water happens to be negative 241.82 kilojoules per mole. And the delta H of N2O4 is positive 9.66 kilojoules per mole. Okay. So, in any chemical reaction, products are formed and reactants are used up, right? So, applying Hess's law to this, we can say, I'll take the enthalpy of formation of any products times their coefficient, since they're formed. And I'll take the negative of the enthalpy of formation of any reactants times their coefficients, and I'll add them up. So this is an application of Hess's law, that basically the enthalpy of change of any given reaction is equal to the sum of the delta H of formation of products times their coefficients minus the delta H of formation of reactants times their coefficients. Does that make sense? So, if I want to solve for the delta H for this reaction, what I'll go ahead and do is I will take my products times their coefficients, the delta H of products, in this case nitrogen, so the delta H of this reaction is, at standard state, is going to be nitrogen delta H times 1. So it'll be 1 mole, and see, that's the thing. These delta H's refer to molar amounts. The delta H of a reaction always refers to the molar amounts, right? So I'll take 1 mole times the 0 kilojoules per mole. Of course, I really don't have to do that because I know it's 0. I could just leave it out. But I'm just putting it there for clarity. And then I'm going to add to that 4 moles times the delta H of formation of water, which is negative 241.82 kilojoules per mole. And then these are my products, so now I'm going to subtract from that my reactants. And my reactants will be 1 mole times the delta H of formation of N2O4, which is 9.66 kilojoules per mole, plus 4 moles, that 4 moles of hydrogen, times the delta H of formation of it, which is 0 kilojoules per mole. So one thing you'll notice is that the moles cancel out, don't they? Moles. And this is why delta H of reaction is only listed as kilojoules. It is not listed as kilojoules per mole. It is listed as kilojoules. So if I take that and subtract it, what do I get for my delta H of reaction? Negative 976?
194.
0.94. Good? Okay. I'll bring my calculator next time to confirm it. Now, do you want to try the capital B on your own? And I can check and see if you get it? Alright, let's do that. Go ahead and try B. I'll write the equation up at the top. You got it?
326.06 kilojoules.
326.06, positive or negative?
Positive.
That sounds about right. Yeah. Because essentially, it would be 2 moles times negative 241.82 kilojoules per mole. And then you would add to that 3/8 moles times 0 kilojoules per mole. And then you'd subtract the reactants, which would be 1 mole times negative 269.9 kilojoules per mole. It's very interesting and rather odd that both SO2 and H2S end up having the same delta H of formation. It's rather unusual. It would be 2 mole times negative 269.9 kilojoules per mole. And that cancels out, moles cancel out. And that's your delta H of reaction. And you said, what was the answer again?
326.06.
Positive 326.06 kilojoules. So that's how you do this problem. It's not hard, it's just a little tedious. Occasionally you may be asked to solve for the delta H of formation of a substance over here, in which case you'd be given the delta H of reaction and have to solve for one of these would be your X, so to speak, your unknown. But it still follows the same general process, same general format. As long as you're thorough in your notation and you're careful putting in your numbers, you shouldn't have any problem with that. Alright, let's take a look at our last problem, although I might throw an additional one at you just for fun. It says naphthalene is a solid aromatic compound often sold as mothballs. The complete combustion of the substance to yield carbon dioxide and water yields about 5,154 kilojoules per mole. Write balanced equations for the formation of naphthalene from its component elements and for the complete combustion of naphthalene. So, let's go ahead and give this one a shot. If I wanted to write the equation for the formation, in other words, the enthalpy of formation equation for naphthalene, how would I do that?
It's going to be a product.
Yeah, naphthalene is going to be a product. Very good. Naphthalene C8H10, or C10H8, right? And that it is a
Gas.
gas. Well, actually, no, it's a solid substance. It's a solid aromatic substance. So this is a solid. Solid. Okay. So now, it's going to be a product. If I want the enthalpy of formation equation, that means I have to form it from what?
Carbon and hydrogen.
Carbon and hydrogen, elements in an elemental state, right? And what's the elemental state of carbon? What's the standard state of carbon?
Just carbon.
Solid, yeah.
Solid.
Basically coal, right? And what's the standard state of hydrogen?
Gas.
Gas. And is it just H?
2.
H2. Yeah, H is not a standard state of carbon. H2 is the standard, of hydrogen. H2 is the standard state of hydrogen. Okay, so now if we're going to balance this, then we need How many carbons?
10.
10. And we need how many H2s?
4.
4. So this would be the delta H of formation equation. This would be the delta H of formation of naphthalene. Now it says write balanced equations for the formation of naphthalene from its component elements and for the complete combustion of naphthalene. So for the combustion equation, that means we're going to start with naphthalene, right?
Yeah.
And what's it going to react with?
Oxygen.
Oxygen. And it's going to produce what?
CO2 gas.
H2O.
And H2O liquid. And the reason why we chose liquid here, because technically speaking, if you burn something, you don't usually see like drop water like spurting out of the fire, right? It usually comes out in the form of a gas. Eventually, though, it does condense. And what it's noticing here is that it says the complete combustion of the substance to yield CO2 gas and water yields 5,154 kilojoules per mole. Because we're given the delta H of this reaction, and because the reaction because the reaction emphasizes the water being a liquid, we have to use that particular value. Alright, so in this case then, if this is our reaction, now we have to balance it, right? So let's balance it.
1, 12, 10, 4.
Yeah, so I got 10 of these, 4 of these, and then 10 O2s plus 4, that's going to give you 24, which means you need 12 oxygens. So you have our balanced chemical equation, right? You guys are champions at balancing, I see. That's awesome.
Yes.
So, I'm going to take credit even though it's not true. No, I'm just teasing. Alright, so now what you're going to do is you're going to calculate the standard enthalpy of formation of this. And in this case, it gives you the enthalpy of the reaction, and you have to look for the enthalpy of formation of this. So this is like one of those other questions I was telling you about. So, if I was to set up this reaction, delta H of the reaction, I would say that this is equal to 10 moles
Times 0, right?
times the delta H of formation of CO2 plus 4 moles times the delta H of formation of H2O goes to, or subtract, or minus 1 mole of the delta H of formation of C10H8 plus 12 moles times the delta H of formation of O2, oxygen. Now, of course, I know that the delta H of formation of oxygen is going to be what?
0.
0. So this can actually just get taken out of the equation. And I'm going to be looking for this, the delta H of formation of C10H8. So I'm going to let this be my X value. Alright? Now, at this point, I have to look at a standard chart, a chart of standard enthalpies of formation to look up the delta H of CO2 and the delta H of formation of H2O liquid. These charts are typically provided in your book, or you can look them up on the internet as well. But your professor on a test would give them to you. It's not something you would have to memorize. Negative 393.5, that sounds about right. And what is the value for liquid water? I'm pretty sure that one should be about 285, negative 285, but I don't know.
Negative 285.8.
Yeah, negative 285.8. Alright, that sounds good. Okay, so we're going to go ahead and use the values for water and the value for CO2 to solve for the value of naphthalene, the heat of formation of naphthalene. So the delta H of reaction here is given as 5,154 kilojoules. And if I have 10 times this, it's going to be negative 3,935 kilojoules. Plus 4 times negative 285.8, which is minus what? 4 times negative 285.8? What's that?
1143.
11 what?
43.2.
1143.2. Okay, sounds good. And that's kilojoules. I mean, it's plus and negative, so I just put subtract. And then minus x. So then basically all you have to do is add these up and then add them over to the other side and then flip it. Oh, and actually it said it yields. So this is technically speaking a negative. This is one of those situations where you have to be careful about the wording. It said it yields 5,154 kilojoules per mole, which means that heat is a product. Heat is a product. And if heat is a product, that means the delta H of the reaction is a negative delta H. So yes, so watch out for that. Plus, as a combustion reaction, heat should be produced, right? So that would also indicate a negative delta H. 5,078.2 kilojoules minus x gives you this, negative 5,154 kilojoules. And then you add that to both sides. And you get equal that cancels out here. And negative x is equal to something over here. Looks like
75.8.
negative 75.8.
Mm-hmm.
And of course you cancel the negative, so x is equal to positive 75.8 kilojoules. Positive 75.8. I can't write today. 75.8 kilojoules. Okay. Kind of sloppy, I'm sorry. Alright, good deal. Well, that's how you would handle one of those problems. Not too bad. Not too bad. Cool. Now, you will occasionally get questions where you have to do some more calorimetry type stuff. Like, for example, is it okay if I erase this?
I have a quick question.
Yes.
So, say that we have O2, I don't know, like solid. That's not the natural state, so that's it's not going to be zero?
No, it would not.
Okay.
You're right.
Alright, that's it.
Good question, yeah. And more likely you'll see something like Cl just by itself instead of Cl2. Because Cl can sometimes exist under certain conditions, but it's very unstable and very reactive. So Okay, cool. So there's one other type of a situation that I'd like to go over with you real briefly, and have you consider. So this is one I'm just going to kind of make up off the fly. So let's say you have, anytime you have a situation where heat is transferred from one system to another, you can kind of solve for different properties related to that system. In one case, you may have, say for example, hot water, or rather, you may have a hot piece of metal placed in cold water. Okay. And when the metal is placed in the cold water, all the heat from the metal gets transferred to the water, right? And in such a case like that, you could say that the Q of the water is equal to the negative Q of the metal. So, yes?
Is it at the same rate? Like the same amount of time? Like one increases and then the other one decreases?
Yeah, I mean, because eventually they'll come to what's known as thermal equilibrium. And thermal equilibrium means they have the same temperature. So heat will continually be transferred, and obviously heat is transferred from hot objects more quickly than it's transferred to cold, hot objects to cold objects more quickly than from warm objects to cold objects. So the farther away, the bigger the temperature decrease, or rather the bigger the temperature difference, the more quickly heat will be transferred. And as the temperature decreases, it'll transfer more or less quickly. But eventually they'll come to the same temperature, thermal equilibrium.
This would be under perfect conditions because the water would naturally lose heat out into like the surrounding.
Exactly. So you could assume in this case that that it would only be true that Q water is equal to negative Q of the metal if no heat was lost to the surroundings. Of course, there will be a little heat lost to the surroundings in the process of putting the hot water. It'll be lost to the air, and then even once the hot metal is in the water, the water can lose heat to the environment outside. But if you have a well-insulated container, those losses will be relatively minimal. And you can still assume Q water is equal to negative Q metal. So let's say you have 45.0 grams of aluminum at 150.5 degrees Celsius. That's placed in 210 grams of water at 25 degrees Celsius, or 25.0 degrees Celsius. What is the final temperature? Conversely, you could also have an unknown metal that's tossed into a calorimeter. The unknown metal is heated up to, say, 150. It's tossed into the calorimeter, and you measure, and it gives you the initial and the final temperature, and you have to calculate what the specific heat is. In a case like that, you can use that type of an experiment to determine what the identity of an unknown substance actually is. Because specific heat is a useful identity property, because most substances have different significant specific heats. Alright, so in this case, you do have to know a couple of other pieces of information, such as the specific heat of water, which is 4.184
joule per gram. Equals C.
Yeah, joules per gram degree Celsius. And you also have to know the specific heat of aluminum, which is 0.903 joules per gram degree Celsius. Or close enough because I made it up. Now I'm pretty sure it's like 0.9 something, but I don't know if it's 0.903. Alright, since this is true, and since these are two different substances exchanging heat, and each of them have a specific heat, what I can do is I could say, I know that Q is equal to M times C times delta T, right? And so what I can do is I can say, M mass of the water times the specific heat of the water times the change in temperature of the water is equal to the mass of the metal times the specific heat of the metal times the temperature change of the metal. So at this point, I can then plug in the information that I have and try to solve for this. The mass of the water in this case is 45 grams. Oh, 45 grams. The specific heat of water is, oh no, the mass of water is not 45, what am I thinking? Mass of the water is 210 grams. Specific heat is 4.184 joules per gram degree Celsius. And the change in temperature is the final temperature minus the initial. The final temperature minus the initial, and the initial temperature of the water is 25 degrees Celsius. Now normally in chemistry we must use Kelvin. The only exception is delta T. If it's change in temperature, it doesn't matter if it's Kelvin or Celsius, because it'll be the same value.
What if the, what's it called? That, the specific heat was in Kelvin?
It doesn't matter because, like I said, change in Celsius is the same as change in Kelvin.
Okay.
Kelvin and Celsius are on the same scale, they just start at a different point. Kelvin starts at absolute zero, and Celsius starts at the freezing point of water. Now, the mass of the aluminum is 45.0 grams. The specific heat of the aluminum is 0.903 joules per gram degree Celsius. And the change in temperature is going to be the final, which is TF minus the initial, which is 150.5 degrees Celsius. Now, there also needs to be, and I almost forgot this very important negative sign is still here, which means it's still here. So at this point, what you in effect can do is cancel out the units of grams and joules per gram degree Celsius because they're on both sides. And you can effectively simplify this perhaps by taking the 210. So it's like 210 times 4.184 divided by 45 times 0.903, and take that and multiply that times TF minus 25 degrees Celsius. And on the other side, that'll be equal to TF, rather negative TF, so it'll actually be negative TF plus 150.5 degrees Celsius. what is 210 times 4.184 divided by 45 and divided by 0.903 give you?
21.62.
What'd you say?
21.62.
21.62. And then I multiply that times TF. So 21.62 times TF minus 21.62 times negative 25. So what's 21.62 times negative 25?
540.5.
540.5. So minus 540.5 degrees Celsius. So at this point, what I'll do is I'll add TF to this side, and I'll add 540.5 to both sides as well. And that will allow me to get all the variables on one side of the equation. So I get 22.62 TF is equal to 691.0 degrees Celsius, right? So then all I have to do to find the final temperature is divide both sides by 22.62. And if I divide both sides by 22.62, what do I get?
30.5.
30.5? Is that reasonable?
Yeah.
Started at 25, it went up about 5 degrees. There's a lot more water than there is aluminum, so even though the aluminum is pretty darn hot, there's not that much aluminum and its specific heat is a lot lower, so it's not going to have as much of an effect on the water. Cool. Well done. Make sense? Cool. There's a few other applications of thermochemistry like that. Some involve heat of reaction, where you do something similar. You calculate the Q of the reaction, and then you divide by the moles of the reactant to get the kilojoules per mole. But it all kind of follows these general principles. So you should be in good shape for thermochemistry.
So, say if the aluminum or the water is impure, do we use the other equation you gave us last time with the calorimetry?
If the aluminum in the water is what?
If the aluminum or water is impure, like not a pure substance?
Yeah, you can, okay, so typically if it is impure, or in the sense of, it'll typically say either assume that the specific heat is the same as that of pure water, in which case you'd still use the same equations, or it would say, it would express it as a calorimeter composed of many parts.
Okay, and then also it's called calorimetry, but we haven't really used many calories yet. We've only been using joules, and I thought that was funny.
Well, you're correct. You're correct. I mean, yeah, 1 calorie per gram per degree Celsius. Yeah, it harkens back to the time before joules was really the primary unit. It comes from caloric, I guess you could say. There's kind of an expression for like heat. But anyway, yeah, no, good point. Good point. Well, thank you so much for coming. I hope this was helpful. And if you have any further questions on any of this, please let me know.